Hello, AP Chemistry, and welcome to Chapter 15, Part 2, where we discuss the concept of K and what it means, right? So first, we loosely defined K way back in Chapter 5 and 19, right, as the relationship of product over reactant, right? Now we can talk about it a little more specifically, right, where we know that K is equal to, right? Oh, first let's get a reference reaction, right? So for this reaction down here, we know that K is equal to, right, products raised to their coefficients, right? So NH3 to its coefficient over N2 raised to its coefficient. Oh, it doesn't have one. And H2 raised to its coefficient. And that's our K expression, right? This is specifically Kc, or K in concentrations, right? Where our square brackets imply molarity, right? In that the only unit that can go into those square brackets is molarity. And that would give us our Kc value for this, right? Bearing in mind that these must be equilibrium concentrations. So they cannot be initial concentrations, right? They must be equilibrium concentrations in order to go into the equilibrium expression, right? Note that on the AP exam, there is literally like always a question that says, write the equilibrium expression, right? And that's all you have to write. That's it, right? Products raised to their coefficients over reactants raised to their respective coefficients, right? Just like there are gimme questions from chapter 14 that say, write the rate law, same thing, right? Just do what you're asked. And note that this is also equal to K forward over K reverse, right? Not to be confused, right? In that Kc, the equilibrium constant concentrations, right, is equal to K, right? The rate constant of the forward reaction over the rate constant of the reverse reaction, right? Note that these are lowercase k's, right? And this is a capital K, right? So be mindful about that, right? What that means, though, is that we can glean a little bit of rate-based information, right? This says that if we have a K that is large being greater than 1, right? If capital K is greater than 1, that means the rate constant for my forward reaction must be bigger than the rate constant for my reverse reaction. Yes, does that make sense, right? That's how that all sort of wraps up, right? If K, the equilibrium constant, is greater than 1, then that means the rate constant for the forward must be greater than the rate constant for the reverse, right? Which makes sense because the rate constant tells us something about the tendency of the reaction to go forward, right? And so if the rate constant for the forward process is bigger, it means it tends to make more product. If it tends to make more product, it's going to give us a larger value of equilibrium constant K. Yes? All right. So again, it is the equilibrium constant, right? So it is a constant. And if we think about what that means, right? If we look at these charts, right, what this says is that, for example, we can start with some reactant, right? So here this says we start with some H2, right? And we start with some N2, and we make some NH3, and lo, we end at those concentrations, right? When equilibrium is reached, meaning the concentrations no longer change, and the rate of the forward process is equal to the rate of the reverse process, right? Or because we could say, right? Likewise, if we start with just NH3, right, because we could just start with NH3, we can produce H2 and N2, right? And you'll note that in this particular graph, what they've done is they've chose a concentration of NH3 that is the same, which means that our H2 and N2 concentrations end up being the same, right? So what that means is K is constant, right? A better way to look at that would be this table from your guys' book. And so what this is saying, right, is that I can start with 0.02 molar NO2, and this is how much of that I end up with, right? And how much that I end up with, right? Which gives me a Kc value of that, where again, K for this is equal to, we're doing this in concentration, right? This would give us our NO2 raised to the second over N2O4. That's it, right? And we get that for our K value. But note, here is the important part, right? If we start with a different value of NO2, right, we get different equilibrium concentrations, which makes sense, right? But this value doesn't change, yes, right? K is constant, right? So what that means is we don't always end up with the same exact number, like in terms of concentration at the end, but the ratio of my concentrations will always give us the same number. as long as we're at the same temperature, that being the one thing that can change K. Yes, does that make sense? All right, do be mindful, right, that there is also the concept of Kp, right? So if we're dealing with gases, we could just as well talk about Kp, where Kp would be the partial pressure of my NO2, right, raised to the second, over the partial pressure of my N2O4, right? Note here, right, we use parentheses because this is pressure and not molarity, right? The capital P means partial pressure of, and then the respective component, right? So partial pressure of NO2 raised to the second power, etc., right? And then your book does give you that equation that relates Kp to Kc, right? And that's just based on our gas laws. But do make sure that you don't confuse the symbolism between our two things, right? It can be one or the other, but not both, right? If the prompt doesn't tell you which one to use, you can use either as long as it's labeled clearly, okay? But if it tells you to provide Kp, right, provide the equilibrium expression, right, in Kp, right, then you must do it this way, right? Otherwise, you'll literally lose a point because you put square brackets on it or something silly, right? So be conscientious and thoughtful about that. All right, and note that here your book does introduce that little note about pure solids and pure liquids, right, where their activities are one, right, meaning that they their concentrations cannot change over the course of time. Because a pure solid or a pure liquid cannot change concentration, right, they are excluded from our equilibrium expression, right? So tuck that away because that becomes very important in just a little bit. All right, magnitude of K is another thing to think about, right? So magnitude, again, just meaning the literal size, right? And we basically have two options. Again, this goes back to what we sort of introduced back in chapter 19, right? Where we talked about K can be greater than 1, right? Or K can be less than 1, or K can equal 1, right? On rare occasion, right? If K is greater than 1, right, bearing in mind that this is loosely the relationship between product over reactant, if K is greater than 1, that means there is more product, yes? The reaction has a tendency to go in the forward direction and produce product, consume reactant. This would mean we have a K is greater than 1, yes? More product than reactant, right? If we have a K less than 1, what that means is that we have more reactant than product, right? Which would be here, so K less than 1, right? Where that means we produce very little product, right? And we end up with more reactant in the vessel, right? We consume very little of the reactant, right? Where this would be something that is more K is not exactly equal to 1, but somewhere in between. Yes, does that make sense? So the larger the K value is, right, the more forward reaction there is, right? Which means that for reactions that go 100% forward, can you think of a reaction that goes 100% forward? Right, strong electrolyte dissociation, right? So for example, we talked about HCl is a strong acid, right? Meaning that when we put it into water, we get pretty much 100% dissociation into this, right? And there is virtually zero HCl still left in the beaker or flask, whatever it is, right? So that would have a K value approaching, ding, 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 approaching infinity, right? Ginormous, because this is essentially zero, right? And obviously there are, there's other criteria there, right? If it all dissociates, there's none there, which means it can never reach equilibrium, right? Which is another way to look at that. But anyway, yeah, let's move on. Magnitude of K. Heterogeneous equilibria, right? What happens when not everything is in the same state, right? Because you'll note that in all the previous ones we've talked about, like, oh, look, all of these are gaseous, right? Because that's an easy place to start. All of these are gaseous. But what happens when that's not the case? Because that's not terribly common, right? So for example, here we have PbCl2 solid, right? And some aqueous things, right? This goes back to what we said about pure solids and pure liquids have activities of 1, meaning their concentrations don't change over the course of time. So when I write the K expression for this, I'm only going to include the things that are not pure solids or liquids. So I'm going to say Kc, because it's aqueous, so that makes sense, right? And I have Pb2 plus and Cl minus squared. That's it. That's my entire Kc expression for this, because we would exclude the solid. Yes, does that make sense, right? And if we think about it being in equilibrium, right, here we have our solid PbCl2 down here, right? In equilibrium with my ions up here. And in order for be in equilibrium, all that has to be true, right? Note that if we think back to language from previous units, right, this would be called a saturated solution, right, where we have added enough PbCl2 that what can dissolve has dissolved, right? The part that dissolves then dissociates, right, producing those ions, right? But there is also still some solid PbCl2 present, and there must be solid present in order for equilibrium to be reached, right? Because that means we have both the forward and the reverse process is happening, right? We have the production of ions and simultaneously precipitation back into PbCl2 solid. Yes? All right, next example, right, is if we have gaseous things, right? So here we have solids and solid and gas, right? So that would mean we might talk about this in terms of Kp, right? And this would be PCO2, and that's it, right? That's what Kp is equal to, which means that if we wanted to measure the K for this process, it actually becomes super easy, right, for this process because there's only one thing to keep track of, right? Same thing applies though, right? If we want to talk about this as an equilibrium process, we must have all species present, right? So if you look here, right, we have a beaker that contains both the solids are present, right? Likewise, both these solids are present. And while this figure is showing you is it doesn't matter how much of each solid, but there must be some of each solid present in order for us to reach that equilibrium, right? And note that we end up with the same amount of CO2 regardless, right? Because that's where the reaction is going to come to rest, right? Yeah, all right. Equilibrium. In the next lecture, we'll talk about the actual calculating of K and manipulations in terms of what we can do with math. All right, make sure you have your calculator for that, and hopefully you have learned how to use the solve function on your calculator, and if not, we might talk about that a little bit. And if we do get there and you're like, what? Feel free to bring it to class and we can chat about it. All right, thank you for listening. Be good, and I'll see you soon. Bye.